I don't know what I've been told.
I don't know what I've been told.
The ACT's the way to go.
The ACT's the way to go.
So prepare and do your best.
So prepare and do your best.
On the ACT test.
On the ACT test.
Sound off.
1, 2.
Knock it on down.
3, 4.
1, 2, 3, 4. 1, 2, 3, 4.
Today is going to be our first ACT test prep session on science reasoning. The test that tests your ability to think like a scientist. Now then, in the words of one of the greatest scientists of all, Albert Einstein, you have to learn the rules of the game and then you have to play better than anyone else. Now then, here's a word right here. You say game. It is a game, guys. It's a competition. You're competing with students from other states, from Alabama, for positions in universities as well as scholarships. So, as in any game, you have to have tactics. Now then, some of the tactics that you need are, and let me tell you, these are tactics for a perfect test. If everything was equal, 35 minutes to answer 40 questions on 7 passages. If you do the math, it's 5 minutes per passage. On average, you have 2 minutes to read the passage and 20 to 30 seconds per question. Sounds pretty simple, right? Well, there's a big old but in it. But all things are not equal, and the ACT is not a perfect test, and science reasoning is not a perfect section. Because you have 3 types of questions: data representation, research summaries, and conflicting viewpoints. Guess which one's the hardest? This one right here. Conflicting viewpoints. Guess which one has the longest reading passages? You got it. Conflicting viewpoints. Guess which one you need to do first? Data representation, not conflicting viewpoints. Conflicting viewpoints, the passage is really long. You can get lost in the passage. There's only 7 questions here. You don't want to spend 15 or 20 minutes reading a passage and figuring it out when you've got these other 2 sections up here that you're probably going to do a better job on anyway. So save conflicting viewpoints for last. Data representation, you'll look at tables and graphs, 5 questions. You should easily be able to get 4 of the 5. Research summaries, a little more in depth, got to know a little bit about experiments and look at different experiments and relate the differences and the similarities. Now then, let's go ahead and look at one of our sample question. The graphs below show the variation of salt concentration, salinity, temperature, and oxygen concentration at various depths in the Bering Sea. Note means parts per thousand. Now then, one of the test strategies that are given to people is that you need to mark up the text. Physically underline it, cross it out, circle things that stand out to you as you read it. Some of the text is going to be pretty heavy, so you'll want to break it apart and try to make sense of it. Important things to mark here. We're in the Bering Sea. You need to know 0/00 means parts per thousand. That's what your salinity is measured in. Now that we've gotten that out of the way, let's go on and look at the question. According to the graphs, how does salinity vary with depth? Well, let's just take a look at the graph. At the surface, your salinity is a little less than 33. At 3,000 meters, your salinity is about 34.2. And it really stays pretty constant from 500 meters down to 3,000. Have a little bit of a decline here, but then you're pretty constant going down. So, choice A, salt concentration is greater at or near the depth. Nope. It's the lowest. Mark it out and move on. Salt concentration increases uniformly with depth. A uniform increase would be a line something like this, if I could draw a straight line. So we can mark this one out. Salt concentration is lowest near the surface and changes only slightly below 1,000 meters. Lowest at the surface here. Here's 1,000 meters. Very slight change. Looks like a good answer to me, but for fun, let's go on and read the last question, the last choice. Salt concentration is twice as great near the bottom as at the surface. No, it's not 33 here. It'd have to be 62 to be twice as great. Mark that one out. And let's move on to the next question. That's a pretty simple question, guys. It's just about a simple analysis of a graph. Next question says, if a diver were rising from a depth of 3,000 meters, here's your 3,000 meter mark, as low as we get, what changes would be registered for most of the trip? Just take a look at your graph. For most of the trip, what's your salinity going to do? Not going to change a whole lot. Decrease a little bit. What's your temperature going to do? Going to increase slightly for most of your trip. What about dissolved oxygen? It's going to decrease. Now then, you've got two decreases: salinity, dissolved oxygen, or going to decrease. Temperature is going to increase. Mark up your test paper, guys, and look at your choices. The water would be getting warmer. Is it getting warmer? Yes. Increase. Saltier? Nope. We've already said it's a decrease. Mark it out. The water would be getting colder, less salty, and richer in oxygen. Is it getting colder? Nope. Getting warmer? Mark it out. Same thing here. It says the water's getting colder. It's not. Mark it out. Let's hope that we've got some right answers down here. The water would be getting warmer. Yep. It's getting warmer. The water would be getting less salty and poorer in oxygen. We've already determined those things when we marked on the graph up here. The answer is D. We're ready to move on to the next question. We're going to run through this one really, really quickly, guys. Which of the following hypotheses would account for some of the information in the graphs? Okay, question number 3. Oxygen enters the water through the surface from the air, but is not carried to great depths. You know, if you just look at this graph, here's your oxygen. Dissolved oxygen levels greatest near the surface. It starts to decrease. You don't have much oxygen at great depths at all. That looks like a really good answer. And you know, you can go on and look at it. Higher temperatures allow more salt. Higher temperature, less salt. No. We've crossed out B. Let's move on to C. C is not correct either. Direct heating of the water by the sun has very little effect on the ocean. Obviously, it does have a huge effect on the ocean because everything changes in those upper levels right there. D, large amounts of salt in solution prevent oxygen from dissolving. Not even a good choice either. We've already got the best choice right here, so A is the answer and you're ready to move on. Now then, certain kind of fish thrives best at a temperature of 3 degrees Celsius. Here's your 3 degrees right here. But I'm going to go ahead and circle this in the answer too because that's an important little tidbit of information. But needs over 34.2 parts per thousand of salt in its water. So it's got to have at least this much salt in its water. Now then, choices. It would have to live within 100 meters of the surface. Absolutely not. We've already said it can't live in this area. It would have to tolerate low oxygen concentration. Yeah, it's going to have to tolerate some low concentration because this is where your oxygen concentration is the lowest. Let's circle this one. Its favorite habitat would be below 2,000 meters. Your temperature is going to be a problem below 2,000 meters. If the oxygen concentration were high enough, it could thrive in any part of the ocean. We've already crossed that out. B is your answer. You're ready to move on. Now then, from these graphs, what general statement? You know, you can stop right here. You got a general statement question right here. Can you make about all the ocean? If you remember from your original reading, this is in the Bering Sea. You cannot draw conclusions about the whole universal ocean by some data on the Bering Sea. So we're always going to look at for things like this. Always increase. Don't make that assumption. Always drops. Nope. Always higher. No. This is really an easy question that they put in here, I think, actually to make you stumble. The answer is none of these, and it's D. And you're ready to move on to question number 6, which can make you stumble a little bit too. And if you get lost in the math, guys, guess at it and move on. But see if you can do it. 5 kilograms of seawater were taken from the surface and then allowed to evaporate so that all you're left with is the salt. Now then, it says at the surface your salinity is 33. Remember what we said at the beginning? Parts per thousand. We've got 5 kilograms of seawater. 33 parts per thousand can also be converted to 33 grams per kilogram. You got 5 kilograms. You just do some easy math there and you come up with C. And you're ready to move on. Here's your answers. This will be posted online so you'll be able to find the answers later on. And the end of our little discussion is another quote from Einstein that says, everything should be made as simple as possible. Don't make it harder than it is, but make sure you don't make it too simple either and miss the answers. Good luck on the test.